All right. So by the end of this lesson, you'll be able to describe how sound waves are heard by the ears, describe difference characteristic of sound waves as perceived by the human ear, describe the different types of interference when waves overlap, and describe what happens when resonance occurs. So, our bell and jar demonstration is struggling. So, we're going to YouTube it. So, what we've got is we've got a bell. Oops. Okay. There we go with that. You got a bell hanging in here in a jar. And then we're going to suck the air out of it. Pretty cool. Yeah? Okay. And then we're going to let the air back in. Oh, no, we're not. We're going to look at the ringing bell. Hold on. See, it's still smacking that. Like whack, 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 whack. Okay. And then we're going to let the air back in. You can now hear the bell. Good with that? So that's demonstrating what? Yes. What's the point of that demonstration? You need a medium for sound to travel. If you scream in space, no one can hear you. Kind of does a kick to like Star Wars and like sci-fi. It's like would not be as cool. Okay.
Maybe in that galaxy though, there's oxygen in space.
Yeah, right. Okay. Um, so a tuning fork um, is a thing that's been manufactured to vibrate at a certain frequency. Okay. So I'm gonna bring it around to your ear.
Is it still vibrating?
Oh yeah.
How long did you do that for?
A while.
Depends on the frequency too, how long it goes.
Yeah.
Oh.
Going behind you.
Oh.
See, it's actually like a G. Where's like G garage band? Give me D sharp. No, D sharp. Yeah. What's this? Garage band. Yeah, it's actually.
I don't hear anything.
Okay. So if the source of all sounds are something vibrating, So in order to hear something, you need something to vibrate.
He
That was
soaked your bag,
flashing,
Gabe.
bro.
He soaked your bag.
It's soaking. Decompensation spider.
Ready?
There's
Oh, dang.
10 kilos of gummies, man. No, that's what you're
One,
doing.
one,
Dude, bro, that water got a crack on my screen.
Right, correct.
That's what happens to people too.
Yep.
So is that a official record?
I was gonna say she has his color. I thought about that. Well, I mean,
I'm starving. I'm hungry. I'm starving. He said he was.
I don't know. I know she's from like.
Oh, yeah, he needs the food.
Oh,
I think I know.
All right. So it's vibrating, and what it's doing is the tuning fork is vibrating back and forth, causing air molecules to be pushed together and then pulled apart, creating this pressure wave, this longitudinal wave, okay, that goes through the air at 343 meters per second, 746 miles an hour. Good with that? Okay. And so your eardrum is on the receiving end, and it goes when high pressure, low pressure, high pressure, low pressure. Like this is your head being pushed in when it has high pressure, and the low pressure is being sucked out. Kind of like, have you ever, like when you're in elementary school taking a sandwich baggie and putting it over your mouth even though your mom told you not to, and you're like, and it's like, okay, and that's what your eardrum is doing. It's responding to the pressure differences. Okay, and so this vibrating eardrum sends signals to your brain, which your brain then interprets as sound. And you can hear me talking. Pretty crazy cool. Okay, I do. Good with that? Okay, bless you. So here is a road down the ear canal. It's pretty kicking music. Ready? Oh dear. This is where you like clean out with your Q-tips, and we're going deeper. This is your eardrum. This is what bursts. It bleeds. It can heal, but it has scar tissue, which isn't good. Yeah.
Thank you.
Okay, if you've ever had trouble with balance, like vertigo or being dizzy, the fluid inside of that stuff, that gets all wonky.
Wait, so can my dad?
No, okay, so if you're deaf, there's a lot of things that could be, I mean, there's a lot of stuff that goes on before you can hear something. So it isn't just like one thing. So no, if you're deaf, you the chances of you being able to balance are pretty high. Like it's not there's a lot of things that can happen that prevents you from hearing. The fact that everybody can hear, that's pretty amazing. Like there's a lot that goes on. All right, so characteristics of sound wave that determine pitch or note. Like, why do you hear a high pitch versus a low pitch? Frequency. Okay, you can feel it in your throat. You talk through a low frequency. High frequency up here is like, okay, you good with that? Okay. The range of human hearing is from 20 hertz to 20,000 hertz. Good with that? Real low. Okay. I wonder if there's a range of hearing video quickly through all the frequencies. 36 seconds? Yeah, we can do that.
You can join my free WhatsApp group and see everything for yourself. Every trade, the exact times I entered and exited.
Adjust your volume. Okay, here we go. There it was.
And during this period in which you're getting deeper and deeper into science, God's not in the picture.
All right. Good with that?
I think so. It's probably that. Gabe's probably like he's 6.
I'm turning the volume down so we don't. Turning it up. Okay. Okay. All right. So there you go. All right. So here's some music science for you. So an octave, like Do, re, mi, fa, sol, la, ti, do, do, do. Those are an octave, okay? 8 notes in between an octave, okay? Every octave, you double the frequency, okay? So if you had any type of music exposure, instruments, you know, middle C is like your foundational starting point, okay? Middle C has a frequency of 256 hertz. The C above that would be what then? 512. Okay. The C above that would be, okay, above that, above that. Okay, so I've got a couple of those, not all of them. Oh, where did that other one go? Oh, edit. Yada, yada, yada. Oh, that's a big one. What is that? Ah, I just had that. There it is. Okay. What I walked around with was middle C. Okay. Okay. This is an octave above. So there's 8 notes in between these two. Hence the oc part. Okay. I have, where did that one go? This little dude. This guy, 4096. Look at that. Okay. So what characteristics of a sound wave happens if there's louder? If you hear, like, what causes it to be a louder sound from a sound wave point of view? The amplitude. Okay. So it's the difference between high pressure, like the bigger difference between high pressure and low pressure. So does it make sense when you go to a concert and you're standing by the speakers, you come out and your ears are ringing? Think about what happened to the eardrum in that video. If you have like high pressure, low pressure, just getting thrashed. It's like screaming, "Why did you abuse me like that?" Okay, and then you just reduce how much hearing you can have when you get older. That's fine. Go hard, die early, right? Okay, so, huh? All right. Actually, get to a place where you can see this on the floor here. Ashley, need you. Oh, grab that in there. Nope. This demo is going to be on the floor, so if you can't see the floor, move so you can. So Ashley, join me over there, just kind of squatting. Okay, what we're going to do, can you guys see this? Probably not. Probably should. Move. Okay, make a wave pulse, kind of like, just like, so do one just like a boom. Okay, so go ahead and do that. Okay, so what we're going to do is we're both going to make a wave pulse and see what happens when they overlap. 3, 2, 1, go. 3, 2, 1, go. 3, 2, 1, go. Okay. You keep doing what you're doing. Okay. Now we're gonna do it in the opposite direction. Okay. See what happens when when they come together. So here's a follow-up question. Do the waves bounce off each other, or do they pass through each other? Okay, ready? 3, 2, 1, go. 3, 2, 1, go. 3, 2, 1, go. Do they pass through or bounce off? They pass through. Good with that? Okay. All right. Thank you, Ashley. Very good. Okay. So when waves overlap, this is known as interference. Oh, it's obnoxious. All right. Let's do this. Okay, so this is constructive interference. Okay, the waves are going are on the same side of the undisturbed medium. Good with that? Experiences constructive interference. So at any moment in time, any moment in time, nice. Okay, we can find the resultant wave pattern. Okay, so at this point in time, I have an amplitude. This guy has an amplitude of +2. This one has an amplitude at this moment in time, also has +2. So the resultant wave pattern is +4. Okay, so you're just adding the amplitudes. Here we have an amplitude, like this moment in time, I have an amplitude of +1 from this guy, and this one I have +2. So at this same moment in time, I'm going to have an amplitude of 3. Good with that? Like right here, I've got like 1.25. This is like 1.75. So this is like 3. Okay, and you can do that at any moment in time. The resultant wave pattern. Okay, if they're going in opposite directions, you have destructive interference, and this you can definitely see how they pass through each other a lot easier. They pass through each other as well with constructive interference. Okay, so if I stop this, if I stop this at any period of time, I can look and say cell phones away, and so here would be this point here, you have +2. Here you have oh, that's too much. Here you have -2. When you combine those together, you get 0. That would be completely destructive interference. Okay. It doesn't have to be completely destructive. Here we still have +2. Here we have minus like 1.5, so you get a +0.5. That's still destructive interference. Good with that? If this one was going down like this, with this one, that would be constructive interference. Even though both are negative, they're both helping each other out. Good with that? Okay. All right, so those are pretty basic wave patterns. You can get some pretty complicated ones. So let's say we have the solid black line, and then you have the dashed black line. The combination of those gives you the gray wave pattern. Good with that? Okay. All right, so what happens when these two waves are overlapping? What's the resultant wave pattern? Have a conversation. Correct answer is? So everybody go with B. You've got +2 plus a -1 gives you a +1. Okay. A little more complicated. What happens when those two are overlapping? Tell your neighbor. Correct answer is A. So here you have +2 plus 4 gives you +6. Here you have +2 plus a -4 gives you a -2. Good with that? Okay. So superposition of waves or resultant wave formation. Where do you see this in life? There's a lot of different examples. Probably in water waves, you can see this interference happening. If you've ever like been motorboating and dragging somebody like in a tube or a ski, and they fall off, and you have to go get them, you like go in a circle, and then when those waves come together in the middle, like sometimes the waves go over the boat as you're picking up the person. You know, I'm talking about yes, no, okay. That's constructive interference. Sometimes, if you ever been riding on a jet ski, wave runner type thing, you're looking like when I've done it, I always look for boats to like jump their wake. But if there's no boats around, you have to make your own. So you like go in a circle, and you try to time it for your wake to come together. And sometimes you nail it. It's like, yeah, it's awesome. Other times you're like what? You're looking back, and there's waves there, and you're like, you didn't nothing. Okay. Sometimes you're gonna get it. You're gonna time it just right where the crests are coming together, the peaks are coming together, and constructive or destructive, like interference. Sometimes you get a peak and a valley coming together, and it's like still water, and you're like, good with that. Okay. So another example would be Okay, we're going to use what we've learned with speakers. Okay, so I've got a stereo that I'm going to hook speakers to. Okay. Okay, one speaker. I'm going to hook a second speaker. Okay. So here's one speaker, two speakers. One speaker, two speakers. Got louder, yes? Okay. Now, what I'm going to do is I'm going to flip the wires. Okay. So I'm hooking them up wrong. One speaker.
This is Carlos Danger, aka the Ginger Ninja, aka the Velvet Cowboy, aka
Okay, one speaker, two speakers. One speaker, two speakers. One. Okay. Putting it on correctly. That's two. One, two. Put it on wrong, incorrectly. One, two. One, two. Okay. No, I'm really right without it. So, thinking about how speakers work. When you hook it up, you got one of them. The diaphragm is the vibrating object, creating sound waves with the pushing, like high pressure, low pressure, high pressure, low pressure, high pressure, low pressure. Okay? When you hook them up together, what we call in phase correctly, they're both currents, they're both experiencing the same direction of current. Okay? And creating different sound waves depending on the frequency it vibrates at. If you hook it up incorrectly, the current is going one way and one direction is going the opposite in the other one. So one's pushing, creating a high pressure, the other one's pulling back, creating a low pressure. And so they are what we call out of phase, causing destructive interference. So you can actually have two speakers be quieter than one speaker if you mess up on the wiring.
Right, so let's say like you had normal one and then the one that's like inverting, you like take away the normal one. What does the other one sound like?
Just like the regular normal one would.
That's weird.
Yeah. Does that make sense? Like it's just, and so this is how noise canceling headphones work. The noise canceling headphones have a microphone in them and they record the outside noise and then they play it in an inverted signal in your speakers. And so the sound waves coming from the outside are overlapped, interfered destructively with the sound waves that your headphones are playing. And so it creates a normal pressure. And on top of that, they play the music you're trying to listen to. It's really cool. Good with that? Okay, interference. All right, so beats. This is not like drop the beat. Okay, it is not this. This is when two similar frequencies are played, causing a fluctuating interference pattern. Me too. Interference pattern. Okay. The equation for that is the difference in the frequencies. Okay. Yeah, you can read that. Okay. So what I have here are two tuning forks that have the same note. Okay, same note. Now, I'm going to put a mass on one of them, kind of make it have a different sound, different note.
Made lower.
Yep, made it lower. Good with that? So, the frequency, or sorry, the beat frequency. Hear that? Okay, that's a beat. Okay, that fluctuating interference pattern. Okay, now based on this equation, what's going to cause the frequency of the beat to decrease? The notes are closer together. Does that make sense? So if I bring them more in tune with each other, okay, previously it was like very frequent. Right? It happened frequently, okay? Hear how the beat is less frequent? Okay? If we bring it more and more in tune, happens less frequent. Okay? If it's too out of tune, it happens so frequently that you can't really, it just sounds dissonant. Okay? Like, does that make sense? It's just so, okay? So you can use this to like tune instruments. Really, like it really helps with like flutes, high pitched things. You can use this to tune your guitar relative to yourself if you're playing with like harmonics and stuff. Okay, so here's visually what's going on. Here you have two sound waves that are going at slightly different frequencies. Sometimes they're in phase with each other and have constructive interference. Sometimes they're out of phase with each other and experiences destructive interference. So you get a loud, so this is the wom, 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 wom. Get with that? Okay. An example in life where you sort of related to this. If you're like at a stoplight in the left-hand turning lane, you've got your turn signal on, and the person in front of you has their turn signal on, and sometimes usually they're not totally in sync, but sometimes it's like yeah, they're out of phase, and you just wait for it. You know what I'm talking about? Yeah, we We all do fun games like that when you're bored. Okay, so got a worksheet due on Thursday.